Assalamu alaikum wa rahmatullahi wa barakatuh. Dear students, today we are going to discuss purification of water. There are different technologies used for purification of water, but today I have selected the topic adsorption for purification of water. And later on I will tell you that why I have selected this topic. Basically, there are some advantages of this topic as well, but still there are a lot of students who requested me to deliver at least one presentation on adsorption. So that is why I have decided to deliver this lecture on adsorption. Keep in mind, in this lecture I will not go through the theoretical details of adsorption. I will directly hit the point, the practical experimental procedures, that what are the steps that you are taking for adsorption, and what are the different steps, different parameters that you are going to optimize during adsorption processes. So there are different methods, as I have told you, for removal of heavy metals, for removal of dyes, for removal of organic toxic pollutants in the water. Like there is a precipitation or coagulation, this the well mature process that are used. Vacuum evaporation, reverse osmosis, membrane separation, catalytic wet oxidation, electrochemical deposition, ion exchange, electrodialysis, electrolysis, ozonation, electroflotation, solvent extraction, and directional freezing. All these end biosorption, adsorption or biosorption. These are different methods which are used for purification of water, and I will try my best to restrict myself to only heavy metals, not to the dyes, not to anything else, only to the heavy metals. So in this way, it will be a little bit easier just to comprehend the whole topic in one presentation. Otherwise, if we are going to discuss dyes, if you are going to discuss heavy metals, some other pollutants, pesticides, just by adsorption, and then if we mix adsorption and biosorption, then it will take a lot of time. And of course, it's even impossible to compile the whole discussion in one presentation, in one class. So I will restrict to only heavy metals, that how to remove the heavy metals. The second point, I will restrict myself to biosorption, not to adsorption. Now keep in mind, there is a difference between adsorption and biosorption. In adsorption, you are going to remove any heavy metals, any dyes, any toxic compounds, or anything by using a material that may be from plants, animals, or that maybe you have prepared in the laboratory. Then we are going to classify that thing into adsorption and biosorption. So if you are using a biomaterial as an adsorbent, then that is called biosorption. So there is a big difference. So if you take some leaves, you dry it, you grind it, and then you are using it for adsorption, so that is called biosorption process. But why I have selected this biosorptions? So there are different reasons. Because biosorbent are low cost. We know that plants are easily available, accessible to every human body, and they have high efficiency. And later on, I will try my best to prove it high efficiency because it have a lot of functional group. It is rich with a lot of functional group. So it have the ability to attract cationic metals and any oxides, anionic one, all of them, they have the ability to absorb all the heavy metals from the water. And the fourth one, it is easily regeneratable. We don't need to even to build an industry for that. We have to grow plants. So on one side, our environment will be free from carbon dioxide. On other side, we can easily use for adsorption processes. And the other function, it's easily biodegradable. So sometimes we are using some oxides and some material, which are, we can say, modern material, perovskite material or any other materials, are inorganic materials. And these inorganic material have the potential to remove the heavy metals from the water. But the problem is their uh, residual residual impurity, we are not going to make it out of the system. That's impossible. But if we compare it with the biosorption process, then it's quite easy and quite convenient that we can easily degrade all these biological compounds. Like if there is a plant or any animal portion like bone, charcoal, or these different things that will be used. And the last one, they have high possibility of metal recovery. And if you go back to the history and find out that who laid the foundation, so the pioneer in this field is Bumel-Velosky. There are different papers. You have a lot of contribution in the biosorption. Here I had given some references that you can go through from water research, international microbiology and biotechnology advancement. You can just go through these different research papers and study it, and there are a lot of information regarding the pioneers and regarding the origin of biosorption. Okay, keep in mind, as I told you, that here I will not discuss the basic theory of adsorption. Here I will just discuss what we are doing in the lab, what's our table work, what is our goal, and what are the parameters that we are going to optimize in the laboratory. So your first goal will be preparation of your material. Now you are using a biomaterial, so that is the preparation of biosorbent. When you had prepared your biosorbent and your biosorbent is now qualified for using adsorption processes, then you are going to characterize that. And that characterization is scanning electron microscopy, energy dispersive X-ray spectroscopy, that you are going to find out that how it look like. What is the size of that particles that I am using for adsorption? And what is the elemental composition of my material, that what is inside it? And the third one is its surface area and pore size. So we are going to find out its surface area. Is it having a rough surface area, smooth surface area, high surface area, low surface area? And what about its pores? It's micropores, mesopores, or nanopores. So what about its pore size? And then we are also finding differential thermal analysis and thermogravimetric analysis, gravimetric analysis. Now these different analyses are for find out the stability of our material, that either our material is thermally stable or not. If it is stable, then what is the range of its stability? So now it depends upon from condition to condition. Sometimes we don't need high thermally stable compounds. We need high efficiency. But sometimes we need high thermally stable particles if we are using at high temperatures. And then we are going to characterize by XRD, FTIR. XRD, I told you in the previous lecture, X-ray diffractometry, that we are going to find out that either our particle is crystalline in nature or amorphous in nature. And what are the functional group attached on the surface of our material? And then PZC, that what is the charge on our material? If I'm using a pH 5, so either at pH 5, my material have a positive charge or negative charge. So it's quite convincing that if there is a positive charge, overall positive charge on the material, then it don't have the ability to attract any kind of positive species due to electrostatic repulsion between the surface and that particle. And then we are switching to the batch experiment. And that batch experiment, we are going to have optimized almost 8 parameters or 7 parameters. The first one is a kinetic study. The second one is a concentration study, pH study, and then temperature study, or we call it thermodynamic study, and then media dosage, particle size, and shaking speed. Inshallah, I will try my best to explain these parameters, that kinetic, how we are going to perform a kinetic study in the lab. What are the basic requirements for kinetic study? And what are the outputs that we are taking from kinetic study? And then concentration study, that why we are doing the concentration study. And what are the basic requirements for concentration study? And what are the output from the concentration study? And see, slowly and gradually we will move to pH, temperature, media dosage, particle size, and shaking speed. Now let's start our journey first one by one. Let's take start from preparation of biosorption. So the first thing that we are taking a native biomass. For example, if you are using a peanut shells or almond shells or any plant or skin, orange peel or any biomaterial. So what are the steps that you are using? So the first thing, that it may possible that what the material you are using, you have taken from some places or from anywhere, it may be dirty and there are a lot of dust particles. So the first thing, we are going to wash it thoroughly in order to remove all the materials, dust particle or oil that is attached on the surface of our biomaterial. And then second is size reduction. Now keep in mind, whenever we are going to wash it, so if it is dry, then it's okay. If it is not dry, then we are going to dry it. When it is completely dried and there is no water molecule inside that, then we are going to reduce its size by crushing it, grinding it. So reduction after reduction of size, we get some granules and some powders. And keep in mind, we have different sieves. They have different mesh units ranging from 50 mesh to 100 mesh, 200 mesh, 300 mesh, 400 mesh, and so on. What is meant by this mesh unit? Basically, mesh unit is like a sieve. It's like if you take a piece of plate and that is 1 square inch. So if it contain 100 pores, so this is called 100 mesh. If you take 1 square inch plate and it contain 200 mesh, 200 pores, so it is 200 mesh. If you take another 1 square inch plate and you make, so that is a 100, and the second one, I suppose that it is 200, and the third one is 400. Now it's quite easy to understand that as the mesh unit increases, size of the pore decreases. Because that is surface area, that is the area of this plate, the first one, the second one, and the third one are equal. But the number of pores is going to increase. So this mesh, so you have 400 mesh, so the size of the particle will be very smaller when it is going to pass through this sieve. Okay, so these are mesh that we are using. Then we have treatment, chemical treatment, but it is directly written over here, a chemical treatment. Basically this mechanism and that schematic diagram I have taken from a review paper that I will share with all of you later on, which was published in 2010, which is regarding the biosorption. So we have a physical treatment, chemical treatment, and thermal treatment. So here I want to discuss the two different kind of treatment: thermal treatment and chemical treatment. Now, whenever our material we reach to this stage, then we are going to subject our material at a temperature, let's suppose at 100 degrees centigrade. So we put our material at 100 degrees centigrade for some time, let's suppose for 3 hours. What happened to our material? Then if our material is stable enough, then we can use. The second, or we are going to make it powder, so then you have to shift from this stage to here. Okay, that is a thermal treatment. Sometimes we are treating at 150 degree, 200 degree. It depends upon on the material that you are using. And the chemical treatment is basically divided into different classes. That is, for example, a kind is acid treatment. So acid treatment means that you have to soak your material in acidic solution, strong acidic solution. And sometimes you are treating with a base, depends upon on our requirement. Okay, what acid will do and what base will do. Basically, acidic solution have a lot of H positive ion. So all these H positive ion will go and attach to any vacancies which have the ability to accommodate that proton. And what is the ability of the basic treatment? The theme behind this is that basic treatment will attract all the protons from the material. Here it's going to give them. Now here it's going to take it. So these are the different, it depends upon on your material, why you are using it. And then you can make the pellet from that or mixer granules. It depends upon on your uh, desired structure, that which structure is more appealing to you. And then we dry that and we use as a biosorbent. So that is quite easy, that you have to follow the whole scheme. Let's suppose I am giving you that if you are using any biomaterial like an orange peel, so first you have to wash, dry it, reduce its size, make its granules or powders, and then you are going to have a chemical treatment. Here you can just browse your internet and find out that what are the methods, what are the methods by which we can treat our material chemically or thermally. So there are a lot of very good research papers who had amazingly explained the treatment, chemical treatment and thermal treatment. Okay, now the first thing that we are going to find out is a point zero charge. But first of all, we should know what is point zero charge. So point zero charge is basically, it's correspond to a pH point at which the surface charge density is equal to 0. And it's play a very peculiar role in adsorption, that is in dissolution rate and also in adsorption. And the reason behind that is, when we know that, let's suppose the pH PZC is 5, then above 5 what will happen and below 5 what will happen. So there must be some electrostatic attraction or repulsion. So that is why it's very important that you should mention, or that you should note over here, that if pH PZC is greater than the pH, then the surface, the sorbent have a positive charge. And if pH is greater than PZC, the sorbent surface is negative. And that's The reference paper, you can go through these different reference paper, and there are a lot of papers who have mentioned that point. What does it mean basically? Basically, it means that if you have a material, and that material you have find out the pH PZC, and that pH PZC is 5, let's suppose. Now, if you are using a pH here 4, 5, 3, 2, or 1 on this range. So, if your pH is less than the PZC, this one, what will happen? The surface have a positive charge. Here the surface have a positive charge. But if you are using a pH greater than PZC, then you are using a negative surface now. So it simply just guide us that if you have found out the pH PZC, then you can remove all the cationic dyes and all the metals positive charged on this range very easily, because there will be a strong electrostatic attraction between the negative surface and positive charge particles. But if you are using that positive charge particle in this range, then of course there must be strong electrostatic repulsion, and that strong electrostatic repulsion will repel the particles to move away from the surface, and there will be no attraction and no adsorption at all. But the question is how we can find out point zero charge in the lab. Okay, now what are the requirements? The first one, you need some flask. That is a glass flask, a conical flask. Minimum you need 7. You can also use some plastic bottle or some other container as well. But as it is easily available in the lab, so for the sake of easy availability, I have used this term that first you need a minimum at least 7 conical flask. And that is that conical flask is of 100 ml is enough. If you are using 100 ml conical flask. The second one, you need an acidic solution. And for that acidic solution, if you are using, let's HCl, you can also use sulfuric acid, nitric acid. We have a variety of acid available in the lab. But for the sake of simplicity, again, I am using HCl. So you need 2 different kinds of HCl solution. One is a concentrated solution and the second one a dilute solution. Later on, I will tell you that why we need 2 different kinds of solution. And here, I will suggest that try to use a dropper, that you also need a dropper for a concentrated solution and for a dilute solution. Your third requirement is you need a basic solution as well. And keep in mind, these solution you are not going to mix with one another, the concentrated and dilute. Okay, in a separate dropper or container, you need a concentrated, that is 0.1 molar solution, or dilute solution, and a dilute solution that is 0.01 molar solution. And you also need a basic solution, and that basic solution is sodium hydroxide, easily available base. And still, again, you need a concentrated one and a dilute one. So till now, what we had discussed, that for PZC, what you have to do, first you have to arrange some glasswares, and that glassware is, the first one is the conical flask, 100 ml conical flask. Minimum you need 7. You can use 8, 9, 10, up to 14. You can use 14 as well. Later on, I will tell you that how you can use 14 and how you can use 7. The second point, you need acidic solution, and that acidic, well, we need different solutions, concentrated acidic solution and dilute acidic solution. The third one, you need a basic solution, and that basic solution will be a concentrated basic solution and a dilute basic solution. The other thing you need, that stirring bar, magnetic stir bar, okay, and that you need according to the number of your conical flask. If you are using 7 conical flasks, so you need 7 stirring bar. Keep in mind your stirring bar must be clinky clean. there must no dust particle or any chemicals attached to it. And there are special procedures for washing that stirring bar, because these are coated with Teflon line, so you can easily wash by using some chemicals like some strong acid solution, and then you sonicate for some time, and then if when all the salts or any chemicals attached to your stirring bar will be removed, then you can just rinse with water, triple distill or deionized water several times, and then store in a airtight jar. The other thing you need plates, and that is a stirring plate. So usually it is available in every lab, in every school, college, and university lab. It's available. Now it sometimes it's multiple stirring plates. Combinedly is also available, and single stirring plate is also available. Both of them depends upon on the availability you can use. So we also need stirring plate in order to put our material on that. Okay, it also have the facilities that you can heat it, because there are two knobs. So basically one knob is used for here you can see here it is for stirring, and this is for heating. It's written very clear over here that this is for stirring and this is for heating. Okay, so this is also we need. But the second point you should keep in mind, here we are using it just for stirring purposes, not for heating. But as a complementary note, whenever you use it for heating purposes, try your level best to double check that either the temperature inside our flask is exactly the same which is shown over here. If you are going to adjust here at 70 degree, it may not be 70 degree inside the flask. Okay, so you have to check it many times. But here we are just using for stirring, so we don't worry about that. What else you need? You also need a salt solution. And that salt solution, that's basically a background electrolyte. That is a sodium nitrate solution. Let's suppose we are using, you can use sodium chloride, sodium sulfate, but I have just taken as a randomly sodium nitrate, and that is a background electrolyte. So these are the things that you need for the experiment of 0.0 charge. Okay, now how to start the experiment? Let's move slowly and start the experiment. First of all, you have to put, these are 1, 2, 3, 4, 5, 6, and 7. These are your 7 conical flasks. And just be sure that all conical flasks are clean and there is no particles, no dust, or no chemicals attached to the walls of that conical flask. Okay. So just put 40 ml of your salt solution. That is the first step in every one. There is no difference that you are adding at 40 ml and other one you are adding 30 ml. Just add 40 ml solution in each flask. The second point, now you are going to adjust the pH. So how to adjust the pH? Now the first one, you have to adjust pH 1. The question over here, that we know that the salt solution that I am using sodium nitrate solution, that is my 40 ml solution, it may possible that sodium nitrate is an acidic salt. So it may have a pH 3 or 4. How to adjust this pH 1? So if you remember, before this slide, I told you, you also need a strong acid solution and a weak acid solution. Just add some strong acid solution and check its pH by using a pH meter. When it is stable, then check it again and just try to adjust the pH 1. Now when you reach to the pH near 1, that is 1.3, 1.4, then you have to use a dilute solution. Because if you are using still a concentrated acid, then it will abruptly change, and that change will be, there will be a big change over there. So try your level best to handle it in such a manner that can adjust the pH according to your required level. For example, if you are adjusting this pH 3, So what you have to do? Again, you have to if I'm using this if your sodium nitrate have a pH 3.5, you don't need to use strong acid solution for adjustment of pH. You need to use a small drop of a drop wise of dilute acid solution, then you can adjust it very easy. So if there is a little bit fluctuation, then you use dilute one. But if there is more fluctuation, for example, if you want to jump from this 3 to this pH 9, you are going to adjust here a pH 9 and your solution is pH 3, then you have to add a strong base solution. So that is the way that we have to play with this. So, but the basic goal is the pH adjustment. So once you are 100% sure that my flask 1 have pH 1, the second have pH 3, the third have pH 5, the fourth have pH 7, the fifth have pH 9, the sixth have pH 11, and the seventh have pH 13. When once you have confirmed that is okay, then you have to add a magnetic stirring bar, and you can see here it's a clean white stirring bar over here. I have just added now. You can see this animation. Okay, so you have to add this, and then you have to add your adsorbents. So now it depends upon your adsorbent that which material you are using. I'm not sure that all of you people are working on the biomaterial and biosorption. Maybe some students are working on adsorption. So you have to add 0.1 gram. It's not 100 restriction over here, compulsion that you use zero point 0.1 gram. You can use 0.5 gram, you can use 0.01 gram. It depends upon on your rest of the experiment that how you are treating that. But just for the sake of simplicity, I had given here that you can use 0.1, 0.1 gram in each conical flask. Okay. When you have adjusted that, then you have to transfer. Now you don't need to add anything else. If you have aluminum foil, you can cover this opening of all the conical flask with a stopper or with the aluminum foil. Okay. And then you have to shift all these flasks to a stirring plate. Like here, you can see here, it's a multi-stirring plate. You can put over here 8 conical flask or 8 glassware at a one time and the speed. So because there are 8 magnets adjusted inside that plate. Okay. So stir at constant temperature, that is at 25 degrees centigrade for 30 minutes. And when you stir for 30 minutes, then what you have to do? You have to find out, check its pH and calculate the change in the pH. Okay. Now that pH you need to find out by using a pH meter. And once again, I want to mention over here that try your level best to calibrate your pH meter after few days regularly. Otherwise, you may face some problems while finding the pH. Okay, so this is a pH meter. Usually, we are using this kind of pH meter in the lab. So you have to check the pH. Now, initially, you have a pH 1, 3, 5, 7, 9, 11, and 13. If you remember, and try your level best to mark every conical flask or every container by writing on this flask, like this is a pH 1, pH 3, pH 5. If you have not written, I'm afraid that you will intermix with one another, and at the end you will unable even to find that which flask have pH 5 and which flask have pH 9. At the initial stage, most of the students make a lot of mistake, like that kind of mistakes in the lab. But I hope that you should be very careful whenever you are handling any kind of chemicals or doing any experiment in the research lab, particularly in the UW lab complex. Because at that time, it's not important that you will be supervised and observed by a teacher over there. So if you make a mistake, you need to repeat the experiment again. So you are going to waste your time. So it's much more better that you should be very careful and you should note each and everything carefully, write it down with yourself, and try to label every flask, every glassware, every conical flask, every stock solution, every material. You need to preserve your material, that is your biosorbent or your adsorbent, in airtight jar. So that's next time you can use it with no modification. So now you have initial pH, and when you have stirred for 30 minutes at room temperature, then again you have find out the pH, and that will be a final pH. But I have not done uh, this experiment, so I leave all these blank for all of you. In order to tell you that you need this kind of graph as well, that you need to draw in your notebook that initial pH, final pH, and then you have to plot change in pH. Okay. Now, when you have find out this change in pH, then you are going to plot this change in pH on your y-axis and this initial pH on your x-axis. What does it mean? It means that this change in the pH is dependent on this initial pH, and you will get this kind of plot. For example, this I have calculated for two different materials. So when you look to this plot, it may possible that this graph is like this. Okay, let me use the pen. It may possible that this graph is like this. It may possible. This may possible that this graph is like this. Okay, and it's also not important that every time it will just intersect the x-axis at this point. It may possible that it is moves like this. Okay, it's also possible that it moves like this. Now, what is the pH? This I have for calculated for one material, and this is for another material. That is, let's suppose our material A, and that is our material B. So what is the pH PZC? Because we have completed the experiment and we have plotted that is change in pH. You see here that is change in pH versus initial pH. We have completed all these requirements. Now what's the pH PZC? Now look at here. For one solution, this pH PZC is this point, this one. That is almost 5.4. So that is the pH PZC. And for other one, you see here, that is this point. That is 6.5 almost. So for compound A, sorry, for material A, we have pH PZC 5.4, and for material B, we have pH PZC this one. Okay. Now you understand the idea that whenever I'm using, let me use one by one. If I'm using this material, this one, that is which I labeled that this is my material A. If I'm using material A, so what does it represent? That is a borderline now. This, sorry, this point is a borderline now, and here we have a surface charge positive, and here we have surface charge negative. Okay, for this second compound, second material, this is a borderline now, and here we have a negative charge, and on this side we have a positive charge. So this is the most important point, and on this point and here on this point, the charge on the material is zero. That is why we call them PHPZC. So that is, so if we want to remove any kind of positive charge particle, so it's much more favorable to use this pH rather than use this pH. Okay. There are also some controversy in different research article as well, but you should just, this is a general idea that you should keep in mind. So once you have optimized, find out the pH PZC, so your one portion is already completed, and try your level best to plot fair every time. You don't need to just modify the data. You don't need to just do rough work every time. Every time your work must be neat and clean. Okay, now the second experiment is our kinetic study. And the kinetic study, we also called it, sometimes we named it as a time study. And for that study, you need different kinds of material, glasswares. The first one, you need a double cell wall beaker. Now, why we need a double wall a double cell wall, a beaker. Basically, we need, it's like a thermostat. There is a water circulation, that water is going, that is inlet on this side, and that is the outlet. So if you are using a 25 degree centigrade and you are performing the experiment in a summer season, that outside the temperature is almost 40 degrees centigrade, then what we need to adjust what is inside that beaker is 25 degrees centigrade. And how we can adjust? By circulating water that having a room temperature 25 degree in this, what is between these two glasses, so they will adjust that. The second one, you need a stock solution, and stock solution is of your adsorbate. For example, if you are going to remove arsenic from this from polluted water, you are going to decontaminate arsenic or cadmium or any other heavy metals, toxic heavy metals, so you need a stock solution of that. Okay. The third one, you need adsorbent, and your adsorbent, if you are using, and this kind of glassware you can use, it's quite convenient that you can use for several weeks or even for months. Okay, so you put your material inside that, and that is the material which is ready for direct use, not the raw material. Okay. And you also need some, okay, let's suppose it is a banana peel. So you have dried it, you have ground it, you have meshed different meshes. So if it have 400 mesh, you just label it like this. It have 400 mesh. And if there is any 300, 150 mesh particles, then you can just keep yourself by labeling like that. Now, it also depends upon on this solution. Let's suppose if it is 100 ppm, so you just label it 100 ppm. Okay. Don't leave any glassware, any beaker or anything which is not labeled. Try to label each and everything what you are using. And the third thing, you also need a stirring bar. Okay, you can use this magnetic stirrer and you can also use this mechanical stirrer as well. Both of them are okay. There is no problem at all. And you also need a pipette filler and also a pipette, that is the nib as well. Okay. You can also use the conventional pipette and also pipette filler. There is no problem in that. Okay. Now what you have to do? First of all, you have to put, let's suppose that is 100 ppm solution. So you have to put 500 ml solution in that. Okay. And just put a magnetic stirrer or put it like this kind of assemblies. Okay. And start stirring. That is a mechanical stirrer. And then calculate that if you are using, let's suppose for 10 ml, you are using 0.1 gram of your material, then for 500 ml, how much I need to use. Okay. And just put that amount of your adsorbent in this beaker, that is a double cell wall, and then start stirring. When you start stirring, so there will be a uniform mixing. And after that uniform mixing, you need to have this kind of table. That table, it means that this column is for time. Okay. So after 1 minute, when you have started the experiment, and after 1 minute, you take some of the samples by using your pipette filler or pipette and pipette filler from here, take a 5 ml from that and store it with yourself. Okay. First, okay, it's very important that you should keep in mind that you cannot store as it is, as you have taken. You have to filter it. And the reason is there is a lot of particles, that is your biomaterial, which is floating and which is moving inside that beaker. That is a double walled beaker. So the double walled cell, it contain a lot of biomaterials. So when we are taking our sample for analysis, so then it create a problem and hindrance. And if we are using atomic absorption, then there is a certain kind of problems. If you are using UV, if you are using another analytical technique for finding its concentration, then it depends upon on our instrument, and it depends upon on the method we are using. So that is why it's recommended just to try to filter it and then store it. And then you have different kinds of uh, samples. The first one you have store for 1 minute. Then after 3 minutes, you take another concentration from that beaker. After 5 minutes, you take another one. And after 10 minutes, then after 15, then after 20, 30, 40, 60, and you continues the whole experimental almost 900 minutes. It may possible that you continue it to 24 hours, or it may possible that you extend then 24 hours up to 48 hours. Okay. So why I have not written here the concentration? Because I don't know the concentration now. The initial concentration of that beaker, I know that I have put over there 100 ppm solution. That was my initial concentration. But this is the final concentration, and that I don't know. If here, let's suppose I have found out that here it is 98. And here I find out that it is 0.98 moles, okay, per liter. Sorry, concentration is mole per liter. That is molarity. And the second one I have found out that let's suppose it is 0.93, and this one is 0.8, okay, 80, and this one and so on. And here I find out that my initial concentration was 100 ppm, or you can just consider here also ppm, then it will be quite easy. Okay, so if I just take here ppm, then it's quite easy to understand that. So initially it was 100 ppm, so now it is 98 ppm. And then here I think let's suppose it is 96 ppm, and after 10 minutes it is 80 ppm. And after 20 minutes, that you need to also find out all these, but for the sake of simplicity, I'm writing this. After 40 minutes, you find out that it is 50 ppm. And after 100 minutes, you find out that you have 4 ppm, let's suppose. ppm, okay, I don't need to write the unit, okay. 150 is also 4 ppm. This is also 4 ppm. This is 3 point, let's suppose 9 ppm. And that is 4 ppm. And so on. Okay, so once you have found out the final value, then you have to find out its x. That is x, absorption capacity, this one. How to find out this absorption? And the unit is moles per gram. Now there are different formulas. Absorption capacity formula, the first one is percent remole. You can just directly initial minus final divided by initial multiplied by 100. For example, if I'm going to calculate for this one, so initial I have 100, okay, and the final I have 98 minus 98, and the initial I have 100. So 100 and 100, it will cancel with one another, and here is 2. So my remole efficiency is 2%. When? After 1 minute. Okay, if I want to find out the remole efficiency after 100 minutes, so then you just check it. Initial I have 100 and final I have 4, so it's remain 96, and this is 100, so it means that we have 96% efficiency after 100 minutes, okay, which remains stable over there. So that's just, I want to give you an idea that you will use the absorption capacity unit in this way. Okay, now the second, but it is suggested to perform the experiment at different temperatures, at 25 temperature degree centigrade, 30 degree, and 35 degree centigrade. Then you have to plot absorption capacity versus time, and I will show you this here, that you got a slope like this. Now initially we know that the speed is very fast, but with the passage of time, this the slope is decreasing, and then the curve become flat. Okay, sorry, and then this curve become flat. Now that's very important that you should note that that why at initial value we have this absorption capacity very high, and after some time we have absorption capacity very low. Initially, our whole active site are free. Our material is free for attachment. And as the particle is coming, the heavy metal is attaching on our biomaterial, then there is a surface coverage, fractional surface coverage. And when we reach to this portion, flat portion, so there is a complete monolayer coverage and there is no more coverage over there. So this kind of graph we can take from, obtain from time study or kinetic study. Now, what is the kinetic mechanism? So basically the rate controlling step in the adsorption, it plays significant role in understanding the mechanism. And keep in mind that the mechanism is basically, if there is a two-phase system, we are using a solid liquid phase. So there is a solute transfer is due to either intra-particle diffusion or mass transfer or both. And there are three steps they are thought to be involved in the adsorption. The first is film diffusion. And what is film diffusion? It's just the adsorbate moves from the bulk solution toward the exterior surface of the adsorbent. Okay, what's meant by the bulk solution? Now, at the interface of our material, adsorbent material, the adsorbate comes in contact to that interface and attached on that material. Now it is coming from the bulk solution where its concentration is very high, where it is completely surrounded by its similar particles, not by anything else. So this is called a film diffusion. The second is intra-particle diffusion, in which the adsorbate transfer within the interior of the adsorbent particles. So that is some interior transfer. We have a porous material and our adsorbate is going to move inside that material. So that is called intraparticle diffusion. And the third one is classified into two different segments. The first one is adsorption of the adsorbate on the pore surface, of the adsorbent. And the second is the chelation between electron donating species, that is oxygen, nitrogen, like that, on the adsorbent electron accepting species, that is adsorbate. But the whole theme, it is a film diffusion, intraparticle diffusion, and the third one is adsorption. And that adsorption of adsorbate on the pore surface of the adsorbent or chelation. So these are the different segments. Now, when we have performed the experiment, then we are going to apply some kinetic models. And that kinetic models are very important for understanding the mechanism and for understanding the rate determining step and for understanding what is happening inside that material and heavy metals. So there are different equations. The expression is, it may be a first order, second order, pseudo second order, pseudo first order, whatever the case may be. But there are some famous models that I have taken from a research paper that later on I will share with you. It's a review paper, sorry, not research paper, it's a review paper. So in some cases, there are second order rate equations. And the equation over here is given that this is a second order rate equations. And this is a CT and C naught. CT is the concentration at the equilibrium at the time, any time. Let's suppose at 5 minutes, 10 minutes, 15 minutes, and that is equilibrium, okay? And that is early applied second order rate equation in the solid liquid systems. And then that is a pseudo first order Lagergren equation. And Lagergren equation, you can sometimes we call it a pseudo first order model as well. And that is absorption capacity at any time, that is absorption capacity at equilibrium. We have to just put in that equation and find out if it equally fits is okay. We have no then we have Alovic equations. The equation is given here, and when this equation is applicable, it means that that is a chemosorption. So what I have just told you before, that basically by implementation of that equation, we can easily find out what's happening inside the beaker, that either it is intra-diffusion, is it a fixed reaction, or it is a not fixed reaction, or it is a first order reaction, or it's whatever the case may be. So it just tells us very clearly. Then we have Weber-Morris equation, Weber-Morris model, and that's model, if it equally fits, then that is intra-diffusion, intra-particle diffusion. And we have also Hu equation, that is pseudo second order equation, like this. We have a general rate law, that's not a fixed order reactions. We can use any of these slowly and gradually. We just try to implement first. If it's not applicable, we move shift to the second one, to the third one, to the fourth one, and so on. Okay, and then the second study, that till now we have studied two things. The first one is point zero charge, and the basic aim of our point zero charge was to find out that what is, at which pH our material have zero charge. That was the first point. The second one, that we have find out that what's the equilibrium time, what's the minimum time required to establish equilibrium for our specific system. And that's called time study, or that's called kinetic study. Okay, if you want to apply the equations, well and good. If you don't want to apply, just to find out that at which time the reaction reached to the equilibrium, is also okay. There's no problem at all. Okay, it's not possible that you can use all the equations in one study. You can use, and it's also not possible that every equation must be applicable. Sometimes one equation must be applicable, the second is not applicable. Sometimes the second is applicable. So it depends upon on your equation, on your material. It depends upon on your experiment and the nature of that interaction. That either it is intraparticle diffusion, either it is chemosorption, or whatever it may be. So it depends based on the adsorption capacity. You can implement any equation, or you can use any equations. Now our third study is concentration study, effect of concentration. And keep in mind, once again, I'm using a 7 conical flask. You can use 7 plastic bottles as well. There's no problem with that. That is a disposable one. You can use once and throw it. But this conical flask, you need to wash it. And the second point, the concentration study, you need to put your material, and that material your adsorbate material. For example, if you are using arsenic, so that is arsenic solution, 5 ppm solution, 10 ppm solution, 15 ppm solution, 25 ppm, 40 ppm, 60 ppm, and 100 ppm. So in the first step, if you just go with me like slowly and gradually stepwise, then you will face no problems in that understanding of their points. First, what you need to do, to take the flask, and then you have to put 40 ml of your solution, and that solution must be 5 ppm, 10 ppm, 15 ppm to 100 ppm. The second point, you need to adjust the pH. And now the pH you are going to adjust. Let's suppose we just have a pH 7. So just adjust all the pH of all the flask as a 7 pH. Okay. And the third one, add magnetic stirrer bar. Now you have already put the solution, you have adjusted the pH, and you have added the magnetic stirrer bar in that. And then add the adsorbent. How much adsorbent you are going to add? Let's suppose you are adding 0.1 gram of the material. Okay. And keep in mind, temperature for this reaction will be constant. It's not the way that you just keep it at 25 degree, the second bottle at 30 degree, and the fourth at 50. No. Okay. If you are using a single plate, and that plate have the ability to accommodate 8 conical flasks, then there is no question like that. But if you are using a separate magnetic plates, then it may possible that for one plate you have to turn on its heating plate, and for other one you have to keep it off. Then after some time, when you collected the data and then you point out that this point is missing, what's the problem? That there is a regular trend till here, but there is some problem over here. So there is no problem over here. unfortunately you forgot to switch off all the plates and keep at 25 degrees centigrade at room temperature. Okay, so now you know the initial concentration, and you know the pH, and you know the initial dose. What we have to find out, we need to find out its final concentration. So initial concentration we have, and the final concentration, you have to find out the final concentration. How to find out? If you are using the analytical tool as a UV, so send your sample for analytical for analysis. If you are using heavy metals, then send it for atomic adsorption or for ICP. And it depends upon on the pollutants you want to remove, that which method is suitable for that. And after that, you need to find out absorption capacity. And when you find out absorption capacity, now basically this is a concentration study, so you have to plot the absorption capacity, this x on the y-axis, and then concentration on the x-axis, and you see you will get this kind of plot. What does it mean? It means that as the concentration increases, absorption capacity increases. Why? Because of the availability of the more particles, more and more pollutants. Okay, so they are going to attach. But after some time, there is a complete coverage over here. That is complete monolayer coverage, and there is no more vacancies for attachment. So the curve become flattened, and when the curve become flattened, then the absorption capacity, we call them as the equilibrium one. Okay, so that's the point, that after which there is no increase in the absorption capacity. So that is another kind of study, that is a time study. If you are performing the whole experiment, you need to just adjust each and everything exactly the same, but only change the pH. That is pH 7 here. I have used pH 7. You can also use a pH 5, and you can also use a pH 3. Just perform the whole experimental setup on pH 3 and pH 5, and you got this kind of curves as well. Now pH 3 I have indicated by a black line, the pH 5 by a red line, and the pH 7 by a blue line. So if we perform at three different pH the same experiments like pH 3, pH 5 and pH 7, so sometime we obtain this kind of trend. It's not important that every time we will obtain the same trend. It may be the reverse of that. That pH 3 may be over here and pH 7 may be over here. Just you can replace pH 3 and 7. But that's not the plotting game. That's experimental games. Sometimes the experimental results show that pH 3 lies over here. Okay, when this is the situation, like it is shown over here, then it means increase in the pH, increase in the absorption capacity. And it's obvious from this figure that pH 3 have the absorption capacity that's here, but pH 5 have absorption capacity here, and pH 7 have absorption capacity over here. So if we perform at different pH, then we got the same results. Now the main point that I want to make over here, that the equilibrium concentration will remain constant no matter we are performing at pH 3, 5 or 7. Here you observe that we have only performed at pH 7, but the same is the case if we are using pH 5, equilibrium does not change. Even if we are using pH 7, equilibrium does not change. Okay, so that's a kind of study that's very important, just to tell us that at which up to which concentration the equilibrium is established. Okay, just imagine that equilibrium concentration is 25 ppm. That's just a hypothetical value. It may be that you are performing the experiment in your labs and this concentration with you may be 100 ppm, and it may be possible that it have a 5 ppm. It depends upon on your experiments, that which kind of metals or which kind of dyes or which kind of uh, chemicals, toxic chemicals you are going to remove. They are pesticides or they are herbicides or whatever it may be. So this equilibrium concentration, it may be 25. Just imagine it's 25. It's not the real data. So okay, till now we have just optimized this as well. The one value, if you go back, we know now our PHPZC. The second one, we know about our time, that what's the time which we can attend the equilibrium. And the third one about our concentration. And the time study, we also called that kinetic study. And this is the concentration study, okay? Now the next one is a pH study, okay? The previous one was also pH study, but that was a part of pH study. Now we can also perform independently the pH study. And for that, once again, I had taken 100 ml conical flask, and that flask, first of all, what should we do? These are almost 7 flasks. So what we do, we just put 40 ml of adsorbate solution. And that adsorbate solution is, about this now, that adsorbate is your chemicals that you are going to remove by using adsorption. Now, the second one, that you have to adjust the pH. How to adjust the pH? Now, keep in mind, now you are not going to adjust the pH as only 7. So the first flask, the pH will be 1. The second pH is 3. The third pH is 5. The fourth pH is 7. And the fifth pH is 9. And then pH 11, and then pH 13. So it means that every flask have different pH. How to adjust that pH? By using concentrated acid, dilute acid, concentrated base, and dilute base. With the help of these 4 different solutions, you can easily adjust the pH of the flask. Now, the second point, then you should add stirrer bar. By adding stirrer bar, basically we means to make the uniform mixing. And after that, our last one, we are going to add our adsorbent, and our adsorbent is maybe biosorption. So we are adding exact equal amount in every flask. And after that, we are shifting our whole setup on the stirring plate, and we placed on that stirring plate up to our optimum equilibrium time, and then we are going to analyze the sample. So basically, now we know that initial concentration is 25 in every flask. You can have a look again over here. That is a 25 ppm in every flask. That's not the case that here is 5, here is 10, here is 100. No, it's 25 ppm in every flask. In the second case, the pH is different. Now the only variable parameter over here is pH. Rest of the parameter is constant. Temperature is 25 degrees centigrade. Media dosage is 0.1 gram. Concentration is 25 ppm, and we had used 40 ml in every flask. Okay, so now when we got this kind of, we have to plot build this kind of table. So the final concentration we don't know. It may be possible that once again I have made a mistake over here. That's moles, but that's not mole. This is 25 ppm, and then you have go to convert into moles per liter and write down the correct value. Okay, and that's mole per liter, not only mole. There's also mole per liter. Okay, let me just make it correct over here, that you should not forget this kind of different corrections in your experiment, in your notes. Otherwise, it will create a lot of problems. So that is also moles per liter, and that's also mole per liter. Okay, so then we are going to find out the absorption capacity, and now you know the absorption capacity can be found out from initial minus final divided by multiplied by mass divided by V and multiplied by 100. That's a formula I had already given to you, that how to find out percent absorption capacity and how to find out absorption capacity. Okay, and then you are going to plot it. Now, when you plot it, you got this kind of plot. That's absorption capacity versus pH, and you got exactly this kind of trend. Now, here will be your equilibrium pH. Okay, and just imagine that your equilibrium pH is 7. We don't know, we have not performed any experiment, but let's suppose you have performed experiment and after that you find out that equilibrium pH. What does it mean? It means at pH 7 we got maximum absorption capacity. Okay, then we have a thermodynamic study, and thermodynamic study means the study at different temperature. So that is why it's also called temperature study. And for this setup we also need a 7 flask, and that 7 flask have different concentrated solutions. That is a 5 ppm, 10 ppm. So first of all, you should just put the 40 ml adsorbate solution. So that is 5 ppm in the first flask, 10, 15, 25, 40, 60, 100. Okay. And then you adjust the pH, and pH may be constant now, because previously we find out that the optimum pH is 7 pH, and then we are adding a magnetic stirrer bar, and after the stirring bar we are adding our adsorbent. So when I am going to add our adsorbent, so that is 0.1 gram, and that's constant. And keep in mind, we perform the whole experiment first of all at 25 degrees centigrade. Now, how to do at 25 degree centigrade? Now it's very easy how to do that at 25 degree. The first one, you take it at the stir plate or and adjust the temperature at 25 degree. If you check it inside the flask and out on the reading is exactly the same, then there is no problem with that. But if show any differences on the reading of the that is on the magnetic stir and the heating plate, the heating plate shows that the temperature is 25 degree, but you find out by using a manual thermometer inside the flask is, let's suppose, 22 degrees centigrade. Then what you have to do, you have to adjust it accordingly, and you increase a little bit. And if you are sure that what's showing to you on the thermometer scale is accurate, then there is no problem. Otherwise, you have to take all your flask and put in that is a shaker, and that is a thermostat shaker. Thermostat shaker is a kind of shaker which contains a lot of water, and you have to put all the flask in a fixed positions. There are fixed position for every flask, you can adjust over there, and you have to adjust the temperature of the water. Then that is a uniform heating. There is no problem at all in that kind of assemblies. Okay, so now and then you have to perform the same experiment at 30 degrees centigrade, and you have to perform the same experiment at 35 degrees centigrade, and then you have to perform the same experiment at 35 degree. So experiment is the same, but you only changed the temperature. The first one is 25 degrees centigrade, the second one is 30, the third one is 35. So when you are going to plot that, you got this kind of plot. Once again, I'm just repeating that here the black line indicates 25 degrees centigrade data result. Okay, because initial concentration we know. The final concentration after sending your samples in case of heavy metals for atomic absorption, ICP, or in case of dyes for UV, or whatever your analytical technique is, just to find out. And once again, there is a problem here, is mole per liter. Okay, it's everywhere it's mole per liter. You just consider everywhere it's mole per liter. Sorry, it's not. It's mole per liter. It's initial concentration and final concentration. That is molarity. So that's quite simple, and there is no problem at all. You should just keep in mind. So the black line indicates the experimental results obtained at 25 degrees centigrade. At 30 degrees centigrade is indicated by a red line, and then at 35 degree is that blue line, which simply mention that the increase in temperature, absorption capacity increases. So which means the experiment, that kind of process is endothermic in nature. While you are performing an experiment which is exothermic in nature, then the trend will be the reverse, not the same. Because with increase in temperature, absorption capacity will decrease. And you will have to expect that all the increase in temperature that you have to got here and here, the different plots over here below in this line. But in case of endothermic, you have to expect the data over here. So that's the difference between endothermic and exothermic chemical reaction. But we have to use some of the equations on that thermodynamic data, and that equation are quite useful. Now, these are different models which are discussed in different review papers. And as I told you that there is a very, not recent review, but it's published in 2010. And that author have mentioned a lot of models like Langmuir model, Freundlich model, Temkin model, DR model, Dubny and Radushev model, and then Langmuir-Freundlich combined model, and then Redel-Peterson model. So there are different models, and every model have some meaning. What's the meaning of that model? If you are going to fit Langmuir model on your data, and it's equally fit, the regression coefficient is 0.99 or 0.98, so it means that there is a mono layer coverage, and that may be a chemosorption, okay. But it may possible that Langmuir is not applicable, is not fit to your data. Then you have to proceed further to use Freundlich model. And Freundlich model is a multi-layer adsorption. And if it is not, then you have to implement Temkin model. And they are different model, tell us different kind of information. It's quite useful. And you have also another complicated models you have SIP model, and SIP model basically just tell us that what is adsorption. In case of Freundlich, Langmuir, DR, Timken, they are quite straightforward and quite interesting. Either it is monolayer, it is multi-layer, temperature effect, there is no temperature like that. But in case of SIP's model, it's really very complicated. The mechanism is complicated. We cannot say that it is a monolayer dominant mechanism, multi-layer dominant mechanism, complete coverage, non-complete coverage, physical, chemical. It's a complex type, okay. And then there is another model, Redke percentage. Redke percentage model is also given here, and it's also a complicated model. And there is a Hahn model and Tooth model and BET model. So there are different model, Brownier, Emmett, and Taylor. There are three different scientists. But here we are not going to discuss these different model. So that is why I'm just touching these different model, that if you are going to perform an experiment and you are interested in implementing the models on your data, then you can use these different models. Quite straightforward. There are the thermodynamic equations that you are using is Arrhenius, Gibbs, one half, and Clausius-Capron, different equations. So, what is the meaning of that? They are different. There are different parameters and equations. Equation of Arrhenius is given over here. Gibbs free energy, and all of these equations you can easily implement on your thermodynamic data. That is apparent activation energy, free energy change, enthalpy change, and enthalpy change. There are different equations, thermodynamic equations, and you can find out the thermodynamic parameter by implementing these different equations. Now, let me just give you a little bit touch to the Langmuir model. So this model is, I told you, is applicable when there is monolayer coverage and all the different sites are equal, energetically equal. So why it's so? It's like an ideal condition, and in that ideal condition, there is no interaction of the particle with one another. So that is why we can easily implement that. So now the equation linear form is like that. So that is the linear form of the Langmuir adsorption equation. If it is applicable, so you can get that kind of results. Now there is another equation of Langmuir called feasibility absorption process, and this also expressed in terms of a dimensional constant, dimensional less constant. Why this is called dimensional less constant? Basically, the equation is RL is given here, like this one. This RL is equal to 1 over 1 plus KCI. And we know that K have a unit, which is a Langmuir binding constant, that is liter per mole. So that is liter per mole, and Ci is mole per liter. Both of them will cancel with one another, and we got a dimensional less constant. Now it's very interesting that when this R value is less than 1, then it means that the reaction is favorable, okay, which is given over here. And when this RL is greater than 1, then that is unfavorable reaction and is not favorable processes. And when this RL is equal to 0, then it is irreversible process. And if it is equal to 1, then it is a linear process. Now let me share with you one of my experimental data that I had removed a mercury on the wheat straw, and then I got that kind of RL value. And I plotted RL versus concentration because if you look at the equation, so we must have to plot this RL versus concentration CI, because K is a constant and CI is the only variable over here. So you have to plot RL versus initial concentration. So when I plotted it versus initial concentration, then what you got this kind of curves. Now this curve is started, this is at 3 different temperature, at 301, 313 and 323 Kelvin. Now, regardless the values of temperature, we look at here that the maximum value is 0.4 and the minimum value is 0.05. It means its RL value, the overall range of RL is less than 1, which simply means that RL is a favorable process. If it is going to cross 1, then it is a non-favorable or unfavorable condition. Okay, then our sixth parameter is adsorbent dose studies. Now till now we have optimized almost 5 different parameters, and now we are going to optimize the sixth one, and that sixth parameter is our adsorbent dose. So first we have to take different flask, and keep in mind every time you have to wash clearly and dry your flask, that there is no contamination in the flask. Otherwise, if there is any contamination of the previous residue in the flask, they will affect your data. So what we have to do next, you have to put 40 ml from a solution, stock solution, which is 25 ppm, because we just consider that experimentally we found that it's 25 ppm is our optimum concentration. Okay, so what we have to do, just added 40 ml in each flask. The second, we adjusted the pH, and the pH is adjusted as pH 7. Sorry, there is again a mistake. This is not pH 5, it is 7. So adjust the pH of every flask, that is from first to flask 7, pH 7. And when you adjusted the pH of, and once again I just remind you that this pH you have to adjust by using strong acid, strong base, weak acid, and weak base solution. This is 7. Okay, weak base solution. And when you adjusted that kind of solutions, so then what you have to do next, you have to add your magnetic stirrers. And we added the magnetic stirrer, and then we are going to add our adsorbent. So now our adsorbent dose is different. This is constant, pH is constant, temperature, which is given here, is constant. All the parameters are constant, just this one is variable now. That is 0 0.5, 0 0.5, 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. So our range is started from 0.05, less than we use normally, and greater than we use normally. So that's a variable. You may not find this kind of study in different research papers, but that is a kind of very interesting research. If you really want to study the different effects, it's full of interest. You can just perform all these different kinds of things. Okay, now you have to just build this kind of table now. Dose, you know about, this is 0.5, and then 0.1, and then 0.1, 2, 3, 4, 5, and 0.6. And the concentration is 25 ppm. Then finally we don't know. If you have to find out, let's suppose this is a 24 ppm, and then that's 20 ppm, whatever the value may be. And from there you have to find out absorption capacity X. When you calculated X, then you have to plot, and your graph must be like this. Okay, it's not, it's like a trend that I'm just sharing a trend with you. It's not important that you got this kind. It may be possible that you got this kind of plot. And then you, this kind of plot, it may be possible. But the trend must be like this. So here is also the trend is like this. Okay, so that is the trend. And the equilibrium dose, we know that this is the equilibrium dose, that when we reach to, we add this amount of dose, we got the equilibrium. Okay, let me share one of the experimental results of mine with you. So here, uh, you know that it is X, it is absorption capacity, and here is the percent removal. So if I just take this one, you can just imagine that when I'm using 0 0.1, 0 0.2, 0 0.3, 0 0.4, and then 0.5, it increasing dose concentration, adsorbent dose, sorry, adsorbent dose. So we know that the absorption capacity increases, percent removal, sorry, percent removal increases, and it reaches to 98%. What about absorption capacity? So, okay, that's what I have plotted. That's not absorption capacity, okay? That percent removal. Because absorption capacity, you have to like this kind of plot. You see from this experimental results here. Okay, there is a lot of mess. Let's remove this. So what we have given here, that is wrong. That's not okay. Your trend must be like this. Why it must be like this? The reason behind this is whenever you are using a small amount of your adsorbent dose. Okay, so if you remember your absorption capacity formula, so there is a difference in the concentration divided by its mass. Okay, so let me just have a quick look to that one, then you can easily understand that. So that is this one. You see here, the absorption capacity X, M is here. So if I'm using a small amount of dose, adsorbent dose, we have a larger X. But as this M increases, this X will decrease. So that's the reason you should just keep in mind this kind of things. Okay. So that's the reason that we have this kind of plot and not this one. Okay, this is again the next mistake. So then we have you have to find out the absorption capacity and plot it. You have the choice to plot absorption capacity versus adsorbent dose or percent removal versus adsorbent dose. Okay, but for percent removal, it's like this. Okay, so that's your choice that you can do. Then we have a particle size study. It's not the last one, but that is the second last one study that we are going to study in the adsorption, that particle size. And I told you that whenever you are preparing your biomaterial, you have to sieve in different mesh units. So some of the particle may be more than less than 400, more than 400. It depends upon on the particle size. So here, first of all, what we do, we put the 40 ml solution in all our conical flask, and that is of 25 ppm. And the second one, we are going to adjust our pH. After adjustment of the pH, that is pH 7 of every flask, we have to add magnetic stirrer bar in every flask, and then add adsorbent. And by adding adsorbent, now we know that our optimum adsorbent dose is 0.1 gram. So we add it in every flask 0.1 gram. Okay, so what's the, but that 0.1 gram is not the same. Keep in mind, it may be different from this 0.1 is from 50 mesh. This is from 75 mesh, that is from 100 mesh, that is from 150 mesh, that is from 200 mesh, 300 mesh, and 400 mesh. It means that as I am moving on this side, size decreases, because increase in the number of mesh is the indication of reduction in the size. As I told you before, that if there is a square inch plate and you make 50 pores in that, and there is another, you make 400 pores in that. So 400 pores, the size of this will be much more smaller than the 50. That's the difference over here. And then you have to plot to tabulate your data in such a way that your particle size is 50, 75, 100, 150, 200, 300, and 400. And your initial concentration is 25 ppm. Your final concentration is I don't know, whatever the case may be. And then you have to plot and you have to get this kind of slope. That's like a trend, not exactly like this, but trend. Why this kind of slope? The reason behind this is, as we are moving in this side, there is a mesh unit, size of the particle decreases. So when the size decreases, absorption capacity increases, because we know that adsorption is directly proportional to the active sides, and active side is proportional to the decrease in the size. If we have a big particle, so the active side may not expose, but if it is smaller, then all of the particle are exposed. Okay, but there is another problem. It may possible that you can get this kind of things as well. It may possible. It may possible that we have hazard manner. So what we have to do, we have to find out the trend and just remove these points. Okay, and then you have this kind of slope. We have to take care of these things. And then the equilibrium particle size, the optimum one must be this one. Okay, then the last one is our shaking speed. Now the shaking speed, we have to take the flask and put 40 ml of 25 ppm solution. 25 is our stock solution. That is the particle we want to remove from the water. And then we have a pH adjustment, and that we know that it's a pH 7, and then we add magnetic stirrer bar, and then we add our adsorbent in every one. And that is, we know that now 100 mesh is our optimum one. So we added 0.1 gram of 100 mesh in every flask. The temperature is 25 degrees centigrade. We have just adjusted on the hot plate like there 25 degree, or we are performing at room temperature, so we don't need to worry about temperature. Okay, then we shift all our flask on the magnetic stirrer plate, and we just try to perform the experiment up to the time at which the equilibrium is established, and that value we are going to take from the time study. So but what we have to do now in this study, because this condition we have already confirmed all these conditions. So RPM, that is if you are using shaker, that is a thermostat shaker, so they have an option that you can adjust 120 RPM, 180 RPM, or 200 RPM, 240 RPM. You can adjust these values. This is the random values I have just written over here, but you can adjust whatever you want. The second point, if you are using a stirring plate, then there is a knob right over there, and from that knob you can easily adjust the speed of that stirring bar, what is moving inside the that flask. So you can adjust. So you have three different, the same kind of experiment you have to done, complete at 120 RPM, or you have to do at perform at 180 RPM, and you have to perform at 240 RPM. So you have these different shaking speeds. Okay, so when you perform all these shaking speed, then you are going to plot the absorption capacity versus shaking speed, and then you can find out that what is our optimum shaking speed. Now let's just remind and revise what we have studied till now. The first one, we started from pH-PZC, or 0.0 charge, or pH 0.0 charge, and we observe that our pH PZC is 5.5. Just imagine it's 5.5. Okay, what you are going to adjust by yourself, it may be possible that your pH PZC is 4.5 or maybe 7.5, depends on your values. Then the second study, or the second parameter that we have to optimize, is time, and we find out that our equilibrium is established in 30 minutes. So the rest of the experiment, if you are performing for concentration study, pH study, temperature study, dose study, so you need to put our flask on the plate, magnetic plate, just for 35 minutes is enough. That's the reason that we just try our level best to perform this experiment first. Because once the time is optimized, then we don't need to wait long for our experimental conditions. Okay, but it may be possible that some reactions are very slow, and you have to wait for 2 hours, 3 hours, and in some cases the reaction, the equilibrium is established even in 10 hours. So it depends up, and sometimes it may possible the equilibrium established in 2 minutes. So that is why we perform this experiment. Then we have a concentration study, and we find out that equilibrium concentration where maximum absorption capacity is obtained is 25. If you remember the graph, then we have a pH study, and I told you that let's just imagine it's 7. It may be possible with you the value is 4, 5, 6, 9, 11, whatever the case may be, and then the temperature. And we know that temperature optimum is 25 degrees centigrade. And then the dose, and the dose we have very different doses, keeping all parameters constant. So whenever you are performing from here to this shaking speed, at a time we can play with one parameter. If you are just performing time study, so rest of the condition is constant, only you can vary time. And if you remember, we have a graph like this. We have absorption capacity on the on the y-axis, and we have time here. But in concentration, we have just replaced this time by concentration. In pH, we have replaced this by pH. And in temperature, we perform this different experiment concentration, but we just do a different pH like that. A different temperature, sorry, like this. And then the dose study, if you remember, we just, so all variable parameter we are putting here, all of them. So at a time, you can just vary one condition. The rest of the parameter must be constant. And then the dose. So which simply means that now we have optimized these 7 different parameters. We have optimized time, concentration, pH, temperature, dose, particle size, and shaking speed. And if you are removing 2 particles, so almost one paper is almost completed. Okay, experimental work of one paper. What about this one? This is just a characterization of your material. Okay, that's not a you can optimize. That's you have to characterize. You have to check that what is the pH, pH, But these are the conditions that you have to optimize. Find out the optimum value for that. And I think is enough for today's. Uh, if there are some students who are still interested in water purification, there are other techniques as well which are used. For example, some people are using radiation technique, and they are bombarding their chemicals by some sort of radiation. They are different radiations, and they are going to degrade the compound, particularly for pesticides and for like that kind of toxic chemicals, organic chemicals. They are going to convert these toxic chemicals into a non-toxic one. So that is also one sort of study. And in that study, you have also to have to optimize time, concentration, pH, temperature, dose, these different study. Of course, there is no particle size and shaking because you are using some sort of radiation. So that radiation you are using with different sort. Then dose is considered as that radiation dose. Okay. And then there are different mechanism for that. So that is also a sort of purification, water purification mechanism technology. People are using radiation technology. There is also another technology that is directional freezing. So directional freezing is a technique used by some researchers. They are going to remove some contaminants and some toxic compounds by freezing the water. Because whenever you are freezing something, so all these materials are just coming to the center, and they have used different techniques for that. And there are also some other techniques like by UV lamp or by some other catalytic degradation or some other techniques. So if you people are interested, then we have to continue. Otherwise, I think it's enough for this water purification or this. Now, okay, that is another scenario that whenever you are going to remove uh, the chemicals or toxic compounds from the water by using your synthetic compound. Here, what we have discussed that I have just today discussed the general pattern, the table work that you are performing in the lab. I had not touched even a single biosorption that which has a high absorption capacity and why it has a high absorption capacity and why if some have low absorption capacity, why it have low. And there is one of very interested research papers which is published recently that is
graphene-based material for purification or for adsorption of water. And I will share that paper in this folder and just have a quick look to that paper as well. That's a really very interesting and very informative paper. So thank you so much. Assalamu alaikum wa rahmatullahi wa barakatuh.